China reportedly is planning to build an undersea complex in the Manila Trench. According to a South China Morning Post report, the construction will pave the way for a sea base of unmanned submarines that would be operated through artificial intelligence. The Manila Trench, an actively moving fault that's located 100 kilometers away from the West Philippine Sea,
Studying submarine landforms and the factors that shape the seafloor is a challenging task. Since these features are deep underwater, scientists use geological data and advanced computer programs to map and understand them. Geostatistical analysis helps researchers to explore how natural processes and environmental factors shape the ocean floor, giving us a better understanding of this hidden world. A pleasant day to each and everyone. Today, I'll be presenting an overview of research focused on the geomorphic analysis of the Manila Trench. This case study shows how GMT, or generic mapping tool, helps in studying the seafloor. By combining GMT with tools like GIS, machine learning, and digital elevation model, scientists can quickly and accurately map and analyze underwater features like the Manila Trench. Deep sea trenches form when one tectonic plate bends into the Earth's mantle while the other shifts to fill the space. Their shape and depth are affected by natural factors. Modern tools make it easier and faster to process data, helping scientists better understand and visualize these hidden underwater features. This research focuses on studying the Manila Trench located in the Ring of Fire in the Western Pacific Ocean. The trench formation is shaped by high seismic activity and geodynamic instability. The study aimed to map and visualize the trench shape, geology, and tectonic features using 2D and 3D models. Statistical analysis was also used to compare data, highlighting differences in the trench structure and depth. The figure shows a bathymetric map of the study area, focusing on the Manila Trench in the South China Sea, west of the Philippines, near the Luzon and Mindoro Islands. This study uses geomorphic mapping and data models with different spatial resolutions to explore the Earth's crust geophysical behavior in this region. The Manila Trench, part of the Manila subduction zone, lies at the boundary between the Philippine Sea Plate and the Eurasian Plate. The Philippine Sea Plate is moving northwest at a high speed, causing the Eurasian Plate to subduct beneath it, and forming the trench, which runs nearly north to south, reaches a maximum depth of 5,400 meters. The next figure shows the geologic map of the Manila Trench. The subduction of the Eurasian Plate beneath the trench is a major cause of tsunamis, which can cause damage in the Luzon Islands coastlines. These tsunamis usually originate from earthquake less than 100 km deep. Research studied the tsunami risk associated with the trench, offering important insights. The subduction also leads to the formation of the volcanic belt along the western side of the Luzon Island. The northern Manila Trench transitions into southern Taiwan, where subduction shifts towards collisions. This northern section of the trench is weakly coupled, affecting the subduction dynamics in the area. The figure illustrates the geoid gravitational regional model of the Manila Trench area. This model reveals how variations in the Earth's internal density create undulations in the geoid, which closely correspond to the structure and shape of the trench. These undulations, shaped by tectonic plate subduction and movement, align with the trench isolines, offering a visual reflection of the Earth's internal processes on the ocean floor. By analyzing these patterns, we gain valuable insights into the connection between the Earth's interior dynamics and the geomorphic features of the Manila Trench. The next figure shows the marine free air gravity of the Manila Trench area. This model emphasizes the importance of precise marine gravity measurements for creating accurate models of the Earth's shape. Changes in gravity anomalies, especially gradients, align visually with the geoid and reflect the effects of continuous geoid movement. These gravity patterns highlight the trench structure and submarine geomorphology shaped by tectonic plate subduction. Such as variations offer valuable insights into the geological process influencing the Manila Trench. The figure presents a 3D map of the Manila Trench created by combining bathymetric and geoid data. It features a 3D mesh plot overlaid on a 2D geoid contour image, forming a block diagram. The model highlights a segment of the trench west of Luzon Island, showing a steeply sloped margin. This visualization helps to better understand the trench structure and key geomorphic features shaped by tectonic subduction. Lastly, cross-sectional transects of the Manila Trench were recreated for the central and southern regions, highlighting key geological features like valleys, slopes, moraines, the South China Sea basin, and the nearby shelves. This profile gives a detailed view of the trench geomorphology, revealing the complex structures shaped by tectonic activity. This analysis helps improve our understanding and the trench formation and characteristics. The Manila Trench lies in the tectonically active zone with frequent earthquakes. Its seafloor features mid-ocean ridges, faults, sea mountains, chains, and plateaus. The trench's geomorphology and bathymetry are shaped by geological, climatic, and tectonic factors. The steepness of the trench increases toward the south, ranging from 25 degrees to 18 degrees north to nearly vertical at 14 degrees north. The tectonic boundary extends into the western Taiwan, marking the active boundary between the Eurasian and the Philippine Sea plate. The histograms of bathymetry for two sections of the Manila Trench show the frequency of seafloor depths along profiles near the South China Sea basin. The different shapes of the histograms highlight unique features of each segment, reflecting variations in seafloor depth. This analysis provides insights into the distinct geomorphology of the trench segments. For this study, the GMT or the generic mapping tool was chosen for its wide range of features, including data analysis, modeling, mapping, and visualization. GMT's strong cartographic capabilities made it perfect for this research on the Manila Trench. It has been used in the previous studies of the area. In addition to GMT, other tools like the phaser diffractometer, data from research vessel cruises, and the DEMs were also used. The mapping process combined GMT data with shuttle radar topographic mission data, while geological analysis focused on modeling seafloor features, mapping tectonic slabs, and identifying submarine volcanoes. The transects of the Manila Trench cross-sectional profiles were digitized to calculate statistical trends for both segments. These trends were compared to approximate the curvature and bathymetric shapes of the cross-sections. The analysis showed differences in geomorphic elevations between the two segments. This comparison helps identify patterns and correlations in the data, providing insights into the geomorphological differences within the trench. The free air gravity map shows large density variations across the study area. High-density materials stretch from northern Taiwan to southern Luzon Island, with gravity anomalies ranging from -50 milligal up to -200 milligal. In the South China Sea, gravity values range from 10 to 30 milligal, while values above 60 milligal are found in the island areas and southern Philippines. These differences reflect the seafloor topography and variations in the Earth's crust and mantle. The southern profile shows values between -50 and -220 milligal, while northern profile shows values from -20 up to +20 milligal, highlighting geophysical differences. The northern profile gentler slope and asymmetric shape suggests local variations, possibly from mantle plumb activity. Additionally, The bathymetric and gravity data suggest that the V-shaped profiles in the deepest parts of the trench may be caused by magma displacement at the trench axis, creating east-to-west asymmetry in the trench shape. The histograms of the bathymetry of two selected segments of the Manila Trench show significant differences in the depth and the shape of it. In the northern part, depth ranged from -4,000 to -4,200 meters with 526 observation points, showing a bimodal distribution including a peak near the Luzon Island. While in the southern part, the trench is shallower with only 142 observation points between -3,500 and -3,400 meters. This comparison shows that the northern part of the trench is deeper than the southern part. The transect of the cross-section profiles shows that the southern part of the Manila Trench has a steeper slope on the ocean side, while the northern part is steeper on the continental side. In the northern segment, submarine terraces are seen at a depth of -2,000 meters, while in the southern part, a gradually sloping terrace is found at a depth between -1,100 and -1,300 meters. Overall, the northern part of the trench is shallower with a steeper slope on the Luzon Island side, while the southern part is deeper but has a gentle slope. This study used the GMT to study the Manila Trench seafloor features, helping us understand the region's tectonic activity and its earthquake and tsunami risk. By using data like gravity anomalies, bathymetry, and geology, the study showed how GMT cross-section stacking method efficiently automates tasks like digitizing, analyzing data, and modeling trends. The research focused on two parts of the trench, revealing differences and providing GMT scripts that can be used for similar studies. In summary, GMT proved to be a powerful tool for studying geological structures and their impacts. This study looked at the difference in the northern and southern parts of the Manila Trench using GMT mapping. These differences are related to tectonic activity like plate collision, which cause earthquakes, volcanic activity, and seismic events. The southern segment has a steeper slopes and greater depths, while the northern segment has a gentler shapes and a steeper slope from the Luzon Island side. This finding show how tectonics and seafloor features work together to shape the region's dynamic environment. Thank you for your time and attention. I look forward to gaining deeper insights and expanding my knowledge in geology, particularly in the areas connected in my course, Geodetic Engineering, as we continue to explore these fascinating interdisciplinary fields.